Alright, so in this video we're going to review a PID controlled balance beam with the objective of balancing a ping pong ball at the center of the beam. As you can see, we start with just proportional control and the ball can't quite get there. That's because P control responds to the ball's instantaneous position rather than the speed of the ball, so it always commands a bit too slowly to strike the balance. While this term is the primary driver of the controller's response, it's a bit too coarse to get the job done on its own. In some systems, steady-state P control manifests as a constant oscillation around the set point, as is the case here, or as a constant offset from the set point, like a DC voltage PID-controlled water heater. The integral term responds to the ball's position over time, so it's capable of eliminating small biases and offsets that continuously exist in the proportional controller's steady state, which aren't big enough to elicit a response from the P term itself. Therefore, it's excellent at trimming small deviations and bringing in the error from an offset. However, as you can see, eye control isn't really appropriate for this application, as it intentionally responds very slowly to the ball's current position, given that it's supposed to remember the ball's positions over time and account for that full history in every contribution it makes, almost like it's responding to the ball's time-filtered position rather than its instantaneous position. The inclusion of integral tends to slow down the overall controller, but often allows for better adherence to the set point. The derivative term accounts for the rate of change of the error. In this case, the rate of change of error is equal to the speed of the ball. This term allows us to slow down the ball when it's running away from the set point, or looks like it's going to overshoot it. Essentially, it dampens the proportional term's massive swings and reduces the speed of the ball when it's close to the center. This term is very useful when you want to use a relatively large proportional gain, perhaps for a faster response, or your system is subject to step inputs from external forces. However, systems can often become unstable when the derivative term is tuned too high, so in other words, when the derivative gain is tuned too high. Derivative control on its own simply tries to bring the ball to a stop, regardless of what the error is. This is because its contribution to the system is a function of the rate of change of the error and not the error itself. Therefore, a derivative controller is not appropriate for this application. We can see that PI control appears to perform much better than individual P or I control, but is still a bit too slow to manage the set point. As mentioned previously, this is because without accounting for the speed of the ball, the controller will effectively treat a very small deviation from the center at high speed the same as one with low speed, when we know intuitively that those two instantaneous responses should be different from a Newtonian perspective, for example, high torque versus low torque. It seems that all three terms have a place in this system: a proportional contribution, an integral contribution, and a derivative contribution. As you can see, full PID control works fairly well, the proportional term responding to coarse deviations from the set point, the integral term responding to small offsets and deviations from the set point in steady state, and the derivative term slowing down the ball to prevent the proportional term from overshooting the set point in its response. And finally, saturation refers to when the controller is operating at its control limits. When this occurs for an extended duration, the integral term can accumulate a significant amount of error and can bias the error in the opposite direction for a long period of time. In this case, externally holding the ball at the end of the beam causes the controller to saturate. As you can see, after the external force is removed, the ball whips to the opposing side and brings the system out of control until the integral term accumulates enough negative error to undo the bias introduced by the external force. Saturation control alleviates this effect by turning off the integral term while the controller is saturated. Not every system wants to control saturation, but in this case, failing to do so results in a large error with a very sluggish response. Full PID control with a saturation treatment allows the system to respond to both step inputs and sustained external forces while exhibiting decent steady-state error characteristics. You can see here that the controller is much better at controlling the ball's speed as it approaches the set point. When an external force is applied to the point where the controller saturates, the integral term shuts off to prevent control variable bias. This is demonstrated by the rapid negative response when the external force is removed. This rapid response is implemented through the proportional and derivative terms. Finally, we have the CAD and code shown at the end of the video. This balance beam assembly was designed in Solidworks and 3D printed on an A1 Mini in PLA. All being said, that should be it for this video. I really appreciate you watching, thank you very much, and I will see you next time.